Let's talk about organic chemistry. This is our second to last chapter in this class. What organic chemistry is all about is it is about the chemistry of carbon. The reason that carbon gets a whole topic all to itself, and in reality there are actually entire degree programs, not just classes, but you can actually get a degree. You can get a PhD in organic chemistry, and even in specializations in organic chemistry. The reason that there's so much devoted to the chemistry of carbon is that carbon is uniquely able to bond with all kinds of things in all kinds of different ways. There are innumerable large and small covalent compounds. And when I say innumerable, it really is innumerable. Like there are literally thousands and thousands of types, different kinds of carbon molecules that we know of, and there's many other thousands that are theoretically possible that we just have never really seen yet. But it is very flexible in how it bonds with things. It can bond in lots of different ways, and it can form many bonds as well. It can form not the most number of bonds possible, but it can comfortably form 4 bonds with other things. And that is a pretty good number compared to other things. There are some metals that under certain situations can form more than 4 bonds, and there are some other nonmetals that under certain situations, again, can form more than 4 bonds. But carbon is always forming 4 bonds. It doesn't have to be under certain situations with only certain other things. It is always forming these 4 bonds with other things. And so it can form all kinds of different compounds. This is why carbon is actually the basis of life as we know it. The DNA that is in your body that has the instructions for how to make you, it is carbon-based. There's other stuff in there too. There's hydrogen and nitrogen and lots of oxygen, and I want to say there's some sulfur in there too, I believe. But anyway, it's mostly carbon. It is carbon-based. The overall backbone of the DNA molecule is made of carbon because of its flexibility in terms of how it bonds with things. So everything that is alive that we know of, the thing, whatever it is, whether it's a plant or an animal or a person, it is carbon-based. Scientists have sometimes theorized that it might be possible that there is a silicon-based life out there in the universe, because if you noticed, silicon is right below carbon on the periodic table. And if you've learned anything from this class, one of the things that I hope you've learned is that if something is very close to something else on the periodic table, especially if it's in the same row as the periodic table, then they probably have similar chemistries. And so it would make sense that there might be some silicon-based life out there. It would have to be something similar to what they had in this original Star Trek episode here, where they had a rock monster that actually turned out, spoilers, by the way, so if you're saying, I haven't seen this show from the 70s, I was saving it to watch it, there's spoilers for this episode. Turns out not to be much of a monster, actually. As with most of these sci-fi shows back then, turns out we were the monsters. But the rock monster from the episode was a silicon-based life form. And that was kind of the big discovery in that episode, was that they were searching for this monster and they could never find it on their scanners or anything, and that's because they were looking for a carbon-based life. And this was silicon-based. It was a living rock. Anyway, so that is part of the reason for the importance of carbon and the study of carbon. So getting back to what makes carbon so special, as we said, carbon is extremely versatile in how it can bond with things. You can get carbon in long chains, like we have here with the propane, which, by the way, this is not really a long chain, actually. This is a really short chain. But you could have carbon chains that go on for literally hundreds of carbons. You can get carbon that can form into chains with branches on it. So you could have a row of carbons, but then you could have another row of carbons coming off of it. You can also have carbon that forms into ring structures. In addition to that, you can have carbon that forms single bonds, carbon can form double bonds, and carbon can form triple bonds. Pretty much any way that we know of, any possible different way to bond, carbon can do it. It is very, very versatile in how it creates molecules. So what we're going to do here is we're going to take a brief look at several different classifications for organic compounds, and your assignment is going to be able to identify the groups of what we call organic groups that are attached to these carbon-based compounds. We're also going to look at some just very basic classifications for hydrocarbon molecules. So we're going to start here talking about that last bit, the very basic classifications for carbon-based compounds. And these are the most basic kind of carbon compounds that you can have. So these are called hydrocarbons. The reason that they're called hydrocarbons is because, as the name implies, the only thing in the molecule is carbon and hydrogen. There's nothing else. We can split this into two smaller categories. So you could have a hydrocarbon that is saturated, or you could have a hydrocarbon that is unsaturated. So what do I mean by that? Well, if you have a saturated hydrocarbon, this is going to be an alkane, and what this means is that every possible bond in the molecule, well, let me rephrase this. There are no double or triple bonds between any carbons in the molecule. Carbon-carbon bonds in these molecules are always single bonds, and what that means is that there are as many hydrogens as possible in the molecule, given the number of carbons in the molecule. So the molecule is saturated with hydrogens. That's where that name comes from. It's saturated with hydrogens. There are no bonds, quote-unquote, wasted on double bonds or triple bonds. They are all used up either as single bonds between the carbons or with hydrogen. A lot of these molecules you are actually familiar with, even though you might not know that they were saturated hydrocarbons. But any just chain of carbons like this, or branched carbons as well, as long as there's no double or triple bonds between the carbons, are alkanes that are saturated hydrocarbons. So you've heard of methane, obviously. That is a saturated hydrocarbon. That is an alkane. And again here, alkane just means that the only carbon-carbon bonds in the molecule are single bonds. That is an alkane. You might not have heard of ethane, but you've heard of propane, I'm sure. Some of you might even have propane in your house. You might have a propane oven or something like that. So propane is just an alkane with 3 carbons in it. Butane, probably heard of that as well. This is also used for cooking quite a lot, or for lighters. So if you have a lighter, I think really any kind of lighter. I don't think that there's one kind that uses a certain kind and something else uses something else. I think any kind of lighter that you have is going to have butane in it as its fuel. Pentane has 5 carbons and is saturated with hydrogens. Hexane has 6. Heptane has 7. Octane, you've probably heard of, once again, if you've ever been outside of your house. Octane has 8 carbons and then is saturated with hydrogens. So there's no double or triple bonds between those carbons. And then we have nonane and decane. And this would keep going as well. That doesn't stop here at decane. This is just where we're going to stop. But hopefully you can see here how the alkanes are just a series of carbons single bonded together, and then all the rest of the possible bonds are saturated with hydrogens. And again, they don't have to be just a line, so we could have carbon bonded to a carbon bonded to a carbon that's bonded to 2 or even 3 other carbons. We could have something like this, and as long as all the rest of the bonds are filled up with hydrogens, and I'm not going to write in the rest of those, but as long as there's only single bonds between the carbons, this is still an alkane. The only qualification to be an alkane is that there are only single bonds between the carbons. Nothing else matters. As long as it's just single bonds between the carbons, it is an alkane. So as we get to larger alkanes, the properties change pretty dramatically. So on the previous slide there, we had up to 10. So that would be, right here. This is the number of carbon atoms. So with 1 through 4 carbon atoms, those exist in the gas state. So methane, ethane, propane, and butane. All of those have to be stored in some kind of container if you want to use them. Even your butane and your lighter, that is actually slightly pressurized. Your lighter is. It's really close to being large enough that it could be a liquid or having a boiling point high enough that it could be a liquid. But it still is going to, if you break your lighter, the liquid that's inside of that lighter is not going to stick around for more than just a few seconds. Like, it's going to evaporate very rapidly. If you get to 5 to 7 carbons, now you get to the point where you have some low boiling liquids, so solvents and gasoline, things like that, where they still are liquids at room temperature, but they're going to evaporate very, very easily. And depending on how warm it is, it could actually evaporate very quickly. This is why things like gasoline are so stinky, is because those the molecules in there are, even though they're, according to their phase diagrams, they should be in the liquid phase, they evaporate very, very easily. They go into the gas phase really easily. Getting into larger hydrocarbon molecules, now we have just plain old liquids, and there's still gasoline at this point. Because if you didn't realize, gasoline is actually a mixture of lots of different hydrocarbons. It is not just octane. There's octane in it, but there's other molecules as well. If you get to larger string of carbons here, 12 to 24, we're still in the liquid phase at this point, but now we're moving on to more intense fuels. So we get jet fuel, portable stove fuel. This is kerosene. If you've ever used a kerosene heater, kerosene is the same molecule as jet fuel. It's just the jet fuel is much more highly purified. The stuff you burn in your portable stove thing is nowhere near as pure as jet fuel, but it is overall the same kind of molecule. If we get to even bigger molecules, up to 50 carbons in the structure, now we get to the point where it's not, almost the point where it's not going to be a liquid anymore, but it is still technically a liquid. So diesel, some lubricants, heating oil, we're getting to a lot more viscous fluids here. It's not like gasoline. Gasoline is almost watery in its consistency, but you get up to things like lubricants and heating oil, it's much more viscous because the molecules themselves are much larger. And then once you get above 50 carbons in a structure, that's a large enough molecule that it can't be in the liquid phase at room temperature anyway. And so those start to become solids like petroleum jelly or candle wax. And by the way, it says 50 plus. This goes up to, like I said, hundreds or thousands of carbons in the molecule. And it will still be solids for all of those. All right. I think we'll call it there for this video. In the next one, we'll pick up with the isomers of alkanes.